Hello everyone, welcome back to the latest lecture session. Let's continue this and get done or finish up the topics that we were discussing in last session. We were discussing water treatment, right? And we looked at home water purifiers for a considerable fraction of our class, and then we moved on to looking at surface water treatment. Surface water treatment, again similar to home water purifiers. What are we trying to do? We are trying to remove the bigger particles by sedimentation, let them settle by gravity. Those that are too small but can settle and take a lot of time though, what do? We try to neutralize the surface charge by adding a coagulant, bring them together to form flocks, and then let them sediment, and then filtration, and then disinfection. Why disinfection? Obviously because we have different kinds of pathogens that can affect the bowel system, right? So bacteria, right? We have that, and viruses. Yes, again I guess now it's the age of corona though, but again you see the shape again with respect to what do we say, viruses, and then protozoa, cryptosporidium, that's something that we are typically always concerned with, and then amoebic cysts, I guess, right? So again different aspects, but you see the shape with respect to the virus, right? Eerily similar to what we always see. Again, we are not going to discuss the viruses and such in detail here. So with respect to disinfection, what is it that we are trying to do now? We see that E. coli or the coliform bacteria should not be detectable in any 100 ml sample when we say maximum probable number, right, MPN. Total coliform bacteria, let us say, right, E. coli and I guess fecal coliform, and here total coliform 2 should be 0, and we also look at trihalomethanes, let us see. While leading to disinfection, they should not lead to high formation of the disinfection byproducts, which are some of which are trihalomethanes, right. So let us see what we have. So typically Indian water after treatment, or in India after treatment at the water treatment plants, typically the standards for E. coli and fecal and total coliform are met. But because of high organic matter, standards for trihalomethanes are not met, and typically the adverse effects of or due to trihalomethanes are in the long term, let us say, right. And another aspect is that though let us say this is the water treatment plant and the sample here is fit with respect to bacterial contamination, by the time it reaches the particular person in his particular tap, let us say, right, a poor attempt at a tap, I guess, right. What do we have here? It does not meet the, I mean if I take the sample from this water, it does not meet the standard for E. coli or fecal coliform. So what is happening? So this is your distribution network, depending on how poorly or well it was designed. Let us say water spends considerable time in this network, and any residual chlorine here might be consumed by the time it spends this much, I mean by the time it reaches your particular home. Or there can be, or is usually the case, sewage network, let us say, above it, which leaks and then contaminates your water network, right. So that is why we have issues at the end of the consumer, let us see. Again we are just pointing out the concerns which can be looked into by the coming or future generations. So chlorine and other forms of chlorine are usually used in India. Typically we use OCl and such, right. This is what people are also using to kill corona. And this aspect I just want to mention or discuss an aspect for a couple of minutes, or rather 1 minute. People are using disinfectants to kill corona. What is this now? This is just hypochloric acid, HOCl, and again what are they doing? They are spraying people. The where is the virus now? It is not going to thrive on the human body, it thrives within the body. Let us say respiratory system, sometimes the gut. Whenever I cough, that is when it comes out, it spreads. So spraying humans with HOCl, which is a strong oxidizing agent, chlorine, HOCl, what are all these now? How do they kill microbes? Again cell wall or RNA damage too, depending on how strong the oxidizing agent is. All these are oxidizing agents, right. So that is certainly going to be harmful to you. right? And I think president of a particular country even asked people to drink disinfectant, and some people also died. But again, that's a sad situation out here. And so spraying on the human body and such, not good. Spraying on the face, remarkably toxic, right? So nervous system will be affected. And the second thing is, you see people spraying roads, spraying, what do we say, temple rooftops and such. You know, a virus that I cough is not going to reach the rooftop, and neither am I going to climb up and catch the roof, let's say, of, you know, this 20 feet high temple or the building, let's say. But people do that. Why? Because people want to typically feel safe by, you know, at least doing something, even though that might or might not work, let's say. And spraying roads, let's say, you know, do you go, you know, virus, you know, rarely do we expect it on the road, and we don't expect it, you know, to be touched by us and then enter our human body, let's say, right? Now, that's not going to happen, but you are having tons and tons of this, HOCl being sprayed out there. And again, it doesn't really kill the virus. Why is that? Because whenever, let's say, you spray it, just spray, not pour, spray it on doorknob or such, let's say, you have organic content on the doorknob, and your HOCl is going to oxidize the organic content and also has to kill the microbe. It doesn't happen, you know. And for you to be able to kill that, you have to be remarkably thorough or pour such a huge amount of HOCl such that you will kill the human beings nearby too. Smell, the fumes, let's say, are remarkably toxic. So again, I don't know when and what the status will be when you are watching this video. So again, don't use HOCl disinfectants and such if you want to stay, free of corona. You know, it's not disinfectant overuse or use, it's just, you know, being healthy, right? Even if you get it, you are going to be able to survive. If not, just use the face mask and wash your hands thoroughly. That's it. Not HOCl. And I can't answer why everyone is doing, because a lot of people do what everyone else does, right? That's one thing to keep in mind. So what do we have out here? Okay, general aspects, no need to look at, but typically I would suggest ozone and UV, obviously because you have relatively less disadvantages with respect to disinfection byproducts, and also relatively more disinfectant, effective disinfectants. But obviously the issue why they are not yet popular in India is because they are costly. Again, we looked at this, and what do we have on the y-axis? It's dose, which is a measure of both intensity or concentration and time, let's say. But obvious advantage with UV is that with just a smaller range of dose, you can kill a greater range of viruses, not viruses, pathogens. But one issue is that there are some critical pathogens that can't be inactivated by UV, let's say. Right, same case with ozone, let's say, at even relatively smaller doses, you can kill most of the pathogens. But as you see with free chlorine, you know, the range of dose required is remarkably high. Keep in mind that this is the logarithmic scale. Same case with chloramines or chlorine dioxide, but this is what people use in India, let's say, again because it is relatively cheap though. Here I guess we have a particular problem to solve, and let us just understand why I also have it, because I want to look at the potency of HOCl vis-a-vis its ability to disinfect or kill corona, I guess, right. Anyway, when chlorine gas is added to water during disinfection of drinking water, it hydrolyzes to form HOCl, right. The pKa of HOCl, the acid dissociation constant for HOCl, right, it is for this, what is this reaction, the Ka will be equal to activity times of the products raised to their stoichiometric coefficients by the activity of the reactants, let us say, right, and pKa is equal to minus log Ka. So, this is how you get an idea about if it is a strong acid, weak acid, so on and so forth, right. Anyway, the Ka is 7.5 now. So, what percentage of the total acid, that is HOCl and OCl minus, total acid meaning total or OCl total is equal to concentration of both HOCl and OCl minus, right, exists in the acid form at a pH of 6 and at a pH of 7, as in what is the ratio of HOCl acid form to, or the deprotonated form to the total acid, right. That is what we want to calculate. So, again I guess it is pretty simple, right. Ka is given 10 power minus 7.5 and we just wrote down the relevant equation earlier. Activity we are assuming is equal to concentrations or the ionic strength is less, and I guess pH is 7 or not 7, here it is 6, that is why concentration of H plus is 10 power minus 6. So, OCl minus will be 0.03 times of HOCl, or you know your pH pKa graph. If this is Ka is 7.5 and your pH is 6, what will most of it be present as? It will be present as the protonated form, right, and the deprotonated form will be I guess relatively less, and that is what you see here. Deprotonated form is pretty less compared to the protonated form. So, from here you juggle it around and such. So, the fraction of HOCl to the total acid is 97% I guess, or obviously you can also solve this from the Henderson-Hasselbalch equation, pH equal to pKa plus log deprotonated form by protonated form, right. You can also solve this. Again all this is just from rearranging this particular equation, let us say, right. So, 97% is present as HOCl at pH of 6, but at pH of 7 what happens now? So, pH 7, instead of 10 power minus 6 I just have 10 power minus 7. So, here now obviously what do we have? pKa is 7.5, and as I move towards pH 7, obviously the fraction of OCl minus increases here. As you see earlier it was pretty low, right, earlier the concentration was low, but at pH 7, and as I move to pH or pH 6, as I move to pH 7, the concentration is now higher, and that is what we see out here. Earlier HOCl fraction was 97% of total acid, and now it is fallen to 76%. So, again when we spray the disinfectant and such, what do you need to look at? One is the concentration of your relevant HOCl, because that is what typically kills or it is the better oxidizing agent, and also secondly the pH. But again, do most of the disinfectants that people use to kill corona, which anyway is not effective, are they maintaining this? Not really. Again I just wanted to point one aspect out. And here is another aspect, considering that the disinfection power of the acid HOCl is 88 times better than its conjugate base OCl minus. We also see that pH has a considerable effect on the efficiency of disinfection, right. So, groundwater treatment, I believe we already looked at this, but what are we typically trying to remove? If it is hardness and we are using it, I mean again keep in mind that TDS up to 500 milligram per liter is very much acceptable, right. If it is much more than that and it is due to calcium and magnesium, I mean hardness, then you will have to remove it, let us see, right. And what else? Eliminate bacteria and provide some residual disinfection, but if it is water treatment units in your home water treatment units, not necessary. But if it is water treatment plants, for example in Mathura and Agra, they pump water from deep municipal borewells, and that is where obviously they have to what do we say, ensure disinfection, because they have to pump the water, I mean from after pumping out and treating they have to send it out over long distances, let us see. But in general in India groundwater is rarely treated, right, typically distributed after ensuring just some level of residual chlorine or disinfectant, let us say, right. And typical treatment technologies for groundwater are based on precipitation, as in we are talking about hardness, groundwater treatment. For example, excess lime treatment, let us say, when you add high what do we say amount of lime, let us say, or you are increasing the pH, you are now going to have precipitation in the form of CaCO3 and magnesium hydroxide, and then you are going to add carbon dioxide to bring down the pH, recarbonation, right. You are adding the lime to increase your or CaOH twice, lime to increase the pH, and then precipitate out calcium carbonate and magnesium hydroxide. You have to increase the pH, and again how do you after precipitation to let the flocks form, coagulation or flocculation, and then clarification or sedimentation, right. After that you add carbon dioxide to bring the pH down, which was relatively higher I guess, and again soda ash, let us say flocculation and such. So, again depending upon the amount of calcium that was present and was added, you will again remove calcium, let us say recarbonation, solids to dewatering, okay, and soda ash, as in you are just going to slightly increase the pH here, I guess. And then what else do we have? Again recarbonation to decrease the pH, and then if there are suspended material, obviously sand filtration or such, let us say, right. So, what are we doing? We are typically trying to remove calcium and magnesium, let us say, right, and then you are going to what is it now, use filtration to supply the softened water here, right. First again, how do we do that? By adding lime, you are increasing the what is this pH, and again same principle, let us say, or in a different application, we are going to remove the residual calcium, let us say in the form of CaCO3, right. So, let us move on. Ion exchange, okay, but on industrial scale and such, we use ion exchangers, let us say, and okay, that is what I guess I always have. So, we use cation exchangers. Why? Obviously because Ca2 plus and Mg2 plus are cations, and in industries, hardness can wreak havoc with respect to their piping and the boilers, that is why we have to remove them. So, what do we have out here? We have hard water containing calcium and magnesium coming in. We have the ion exchange resin, upon which you have sodium, let us say, initially present, and calcium and magnesium greater charge density, they are going to displace Na plus, let us say, that is why they are called cation exchangers, and Ca2 plus and Mg2 plus are going to be adsorbed onto this particular ion exchanger, and they are going to be removed. Okay, here we have the legend magnesium and calcium, right. Magnesium and calcium are coming in, they displace the sodium, and then sodium water, softened water with just sodium comes out. But after some time, obviously the ion exchange resins, all the ion exchange resins, let us say, have been used up, or there are no more sites for ion exchange, and then what do you do to regenerate? You pump in Na plus concentration at very high, or pump in Na plus at very high concentration in the reverse direction, right, brine solution containing sodium, and that is how you are going to recharge the relevant resin and reuse it, right, and then you will reuse it. Again, let us keep them. So, typical ion exchangers, you can see what it is that we have, 500 to 900 mm in diameter, I guess it should not be mm, I guess this is an error that you can see out here, right. Okay, and ion exchange for hardness removal, this is how we have industrial scale ion exchangers. But one other aspect is, in groundwater we know that we have arsenic and fluoride, and we know that in India many people use hand pumps, let us say, right, for getting the water out, right, poor attempt at a hand pump. So, how do you, what can you do here, let us see, right. Let us see what we have. There are many options available, but costly, right, and that is where they fail typically. Let us look at some of the most widely used techniques. Surface complexation and adsorption, as in you use an adsorbent upon which arsenic and or fluoride can complex and adsorb. Let us say it is adsorption, not absorption. You have surface sites here where arsenic or other compounds can adsorb depending on the type of adsorbent. Mostly widely used and which is recommended by World Health Organization is activated alumina, and it is low costly too, and it is relatively proven. Another thing is ion exchange, but the issue with ion exchange is, let us say I have other compounds too, as in what do I have here? Let us say arsenic, let us say in different forms, AsO3 3 minus I think, and AsO4 3 minus I think again charge, again negatively charged anions typically, let us see, right, at most pH I think this is what they are in, or with change in pH you will have slightly different speciation. But in water, what else will you have? You will have SO4 2 minus, you will have CO3 2 minus or HCO3 minus, other anions present, not Cl minus, that will not be really concerned here. So, the key is to use an ion exchanger that will solely remove arsenic and not remove the other usually present compounds, because arsenic is present at very low concentrations. I think 50 or 5 ppb was the standard or drinking water limit. Typically you will have these in ppm, almost 1000 times higher concentrations. So always in the market, or there is always this researcher who comes up with this ion exchanger which can remove 100% of arsenic. Well, many ion exchangers can do that, but the key is being able to regenerate, and more importantly being able to come up with an exchanger, what is this now, anion exchanger, that can or that is preferential to arsenic, let us say, right. So that is something to keep in mind, and let us move on. So let us just understand the basics. Here we talked about, not here, earlier we talked about Henry's law, where let us say you have a system, let us say I have a compound out here, that is dissolved in water, and depending upon its tendencies to leave the water or stay in the gaseous phase, some of the compounds that were present only in the water, now they will move into the gaseous phase, and the law that gives us an idea about the ratio of the concentration in the gaseous phase to the aqueous phase, it is Henry's law, right. So that is what we have out here, right. I guess I should not have mentioned Kh, it is K, right, concentration in the aqueous phase. So similarly, compounds, let us say they would want to be adsorbed onto different materials, let us say, again it depends upon the kind of compound and kind of adsorbent, but we are not going to get into that. So different affinities, let us say, for different compounds and different adsorbents, but some will stay in the solution, or some of it, but depending on the type of compound, some of it will also be adsorbed onto it. So the concentration that is adsorbed onto the, or the compound that is adsorbed onto the adsorbent, that is Q, milligram of the compound adsorbed per, let us say, kg or gram of the adsorbent. K is a constant, again 1, N is also not constant, depends upon the relevant property of your particular system. Here C is the concentration of the compound, pardon me, in your aqueous phase, right. So you can look at the similarity with respect to the Henry's law. Again, here different phases, here it is aqueous and gaseous, here it is aqueous and let us say, if I can say so, the solid phase, I guess, right. So that is what we have. Example of, it is just an example of a model to explain the phenomena which is adsorption, let us say, right. That is the model we are using. So again, what is it that WHO typically recommends? You have water being pumped out from the ground and it goes through, you maintain a head of water. Here you have granular activated alumina, as we mentioned earlier, that acts as a good adsorbent, I guess, for arsenic and or fluoride, right. And you have coarse sand pebbles, coarse sand and pebbles, and then the water will come through and is collected here, arsenic free. But obviously the issue is what to do with this granular activated alumina after it is consumed, as in over time all the active sites on your activated alumina are going to be used up. What to do, and how does the relevant layman or the villager know that this cartridge has been exhausted or such, let us say, right. So these are some of the minor challenges. Again, you can look at this, it has been used since 1940s, the way to prepare and so on and so forth. But one issue is that all these adsorbents, they typically have high surface area, right. Here we have 350 meters square per gram of the media, right. As in, you can think of your football field, let us say maybe 100 and 90 maybe. So what is this? 9,000 and 350 meters square per gram itself, right. So that is something to keep in mind. Just per 1 gram you have 300 meters square of surface area, right. And adsorptive capacity, again it is dependent upon the pH because of surface complexation and so on and so forth. And fluoride is best adsorbed at 8.2, where we have a point of 0 charge, where alumina surface has a net positive charge, I guess. Okay, let us move on, generic stuff. So let me see this. Okay, but how do I know, when it has been exhausted? That is called the bed volume, the total volume that is treated before the media needs to be regenerated, let us say, right. That is what we have, our bed volume. So, adsorb to equilibrium, let us say. Initially this is what we see, you have the different pores and such. It is not just the surface, you have multiple pores, right. You have multiple pores here. Initially yes, and adsorption more and more often, later we reach equilibrium. All the adsorption sites have been filled up. Initially has the equilibrium been reached between the aqueous phase and the adsorbent? Not yet, but here we have reached equilibrium, let us say, right. So, that is what we saw earlier, let us say. This is the adsorbent surface. So, adsorbed molecule and diffusing molecule, let us say, right. And one aspect here is, how do we know when to regenerate or such? What is going to happen, let us say here is the volume of effluent that is coming through that hand pump, right. And here you have activated alumina, let us say, and here we had arsenic free water. But I need to be able to tell the villager, when does he need to throw it out and start, or getting or regenerating this alumina, or getting a new alumina filter. What do we do? See now, as arsenic filled water is coming in, at this stage after V1 bed volume or volume of effluent has been passed, only this level of alumina has been what do we say, consumed, if I may say so, right, and only some of it has reached equilibrium with the arsenic in the groundwater. But as I keep pumping in more and more what do we say, water, what do I see? More and more of the alumina filter has been what do we say, or is now in equilibrium with arsenic, right. And here exchange is still taking place in some zone, and virgin alumina is present in only some virgin alumina is present. Virgin in the sense that fresh alumina, let us say, right. And after some point obviously you have exhaustion of most of your particular alumina and you have a breakthrough, right, where it is let us say if your 50 ppb is this, maybe it is now at 75 ppb and it is not acceptable to you. And then finally all the alumina, let us say, has been used up, and that is why you see the concentration in the effluent or the treated water is the same as the concentration in the influent water. That is what you see. Initially this is what you have, and after all the alumina has been used up, the concentration in the effluent or the treated water will be as high as the concentration in the influent water. So, what do you need to see? You need to be able to predict when this breakthrough will occur and then have to change this activated alumina filter, let us say, right. So, let us move on to these aspects. Practical challenges are when to identify if it has been exhausted and it needs regeneration, let us see. Again general aspects. So, I am going to move on with these aspects, I guess. Empty bed contact time, as in the water has to stay in contact with your adsorbent, let us say, so that the molecule can diffuse onto the surface or into the pores and get absorbed onto the pores, let us say, right. I have different pores and such out here. The water has to, or the molecule has to diffuse into it. That is why I need to provide a contact time, let us see, right. Again, these are some of the practical challenges. Okay, so looks like I am out of time, and I wanted to talk about the RO and why it is not good for India, and I guess we will have that discussion in tomorrow's session, and thank you.